Welcome to another Unreal Engine tutorial where we will explore the fascinating world of ocean simulation using FFT or Fast Fourier Transform to create realistic waves with foam. Now we will break down some key formulas without diving too deep into the complexity, just enough to understand the basics. Let's dive in. In ocean simulation, two crucial components are required: statistical wave models and fast Fourier transform. Statistical wave models are mathematical representations that describe the statistical distribution of wave characteristics within a specified area over a given period in oceanography. Fast Fourier Transform is an algorithm designed for efficiently computing the discrete Fourier transform. Why do we choose FFT instead of DFT? DFT takes n squared time, while FFT is faster with n log n time complexity. As illustrated in the graph, the growth rate of n log n is significantly slower than n squared, especially with higher n input value. This is the formula of DFT derived from Fourier transform and Fourier series. Use of imaginary numbers come from converting sine and cosine function to exponential using Euler formula. DFT serves as a tool to transform wave signals from the spatial domain to frequency domain. IDFT accomplishes the reverse, transforming signals from frequency domain back to the spatial domain. Why do we perform these transformations? The benefit of representing waves in the frequency domain is that it enables us to manipulate and control their characteristics more effectively. Meanwhile, the spatial domain is where we show how waves appear on textures and material. Several FFT algorithms are available, each suitable for various use cases. One well-known FFT algorithm is the Cooley-Tukey algorithm. The process involves splitting the sequence of n data points into odd and even halves. Recursively compute the DFT for each half, and then combining the result to form the DFT of the entire sequence. The twiddle factor represented by W is an exponential used in this process. Here is a visual representation of the Cooley-Tukey algorithm. We create a statistical wave model using the Phillips Spectrum models, a mathematical representation of the statistical distribution of wind-generated ocean wave heights. To introduce variability, we include random complex amplitudes into the waves, simulating the complexity of ocean wave patterns. In the time domain, we generate two waves propagating in opposite directions, left and right. This temporal representation captures the evolution of wave characteristics over time. To create our complete statistical wave model in the space domain, we combine many waves through the superposition method, reflecting the distribution of waves across physical space. In the context of ocean wave simulation, a cascade refers to a specific layer or level of wave components within a multi-resolution simulation framework. This tutorial uses 4 cascades, named from Cascade 0 to Cascade 3. The idea is to simulate larger scale features separately from smaller scale details. By combining these distinct simulations, we get a realistic representation of the overall ocean surface. Render target A is used to store 4 derivatives, while render target B holds 2 derivatives along with representation of foam and surface stretch. An additional pixel render target is used to capturing roughness. 2 vertex render targets are used in our simulation to store world position offsets. To offset vertices in an ocean surface mesh, modifying vertex positions directly in the vertex shader is more efficient than modifying the mesh itself. We use the GPU compute capabilities of Niagara system in Unreal Engine for simulating ocean water. The overall process involves initializing parameters and render targets, then update animation time using data time, generating a wave field in the frequency domain using the Phillips Spectrum with random disturbance, updating the wave spectrum to simulate the evolution of wave field over time, apply IDFT to transform wave spectrum from frequency domain to spatial domain, and finally export data to render targets. This combined approach allows us to achieve realistic and dynamic representation of ocean water within the Unreal Engine environment. In the next video, we will create this ocean inside Unreal Engine 5.3 using that CG's tutorial. Thank you very much for my Patreon members and all my YouTube channel subscribers who are supporting me. See you in the next tutorial.